Hello, welcome to my channel. Welcome to Rehandran. In this video, we're going to talk about circuit response, time and frequency domain analysis. So, in the previous video, I discussed about RC response of the circuit when DC source is connected. Now, I'm going to talk about RL response for sinusoidal input. So what will happen if we input a sinusoidal to a RL circuit? Now let's get started. So let me first draw the circuit. So drawing the circuit. This is a series RL circuit, and say this is, and the input is Vm sine omega t. This is R, this is L. Assume that it has initial current IO, this. So we are gonna what we are gonna do is we are gonna analyze this circuit in time domain. So time domain analysis. So let us so what we know from circuits, from signals and systems point of view, that RL circuit is an LTI system abides by superposition principle, due to which we can apply KVL KCL. So for convenience we will use KVL, so for loop current. So for loop, R plus L d by dt it equals the input. So the input here is Vm sine omega t. Let us address this as Vs because I have denoted the Vs in the previous lecture, so it will be helpful in some way or another. So what we are getting is a differential equation with constant coefficient. This R and L are constants. So let us now replace d by dt with linear differential operator, which will give R plus L d it equals Vs sine omega t. Now we have found our differential equation. We are gonna solve it. So for for complementary complementary solution, we are gonna we the equation R plus LD is equals to 0. Okay, this is also the characteristic equation of the LTI system, RL circuit. Okay, so from the characteristic equation we are gonna get the eigenvalues, which is the value for the solution of which is the value for complementary solution, which, and the complementary solution is the transient response of the RL circuit. So d equals minus R by L. So we know that all kinds of complementary solutions for linear differential equations are of the form y equals summation c1 e to the power lambda 1 t. Okay, ci. Okay, so ci I equals 1 to but n. Okay, this is the uh, form for the complementary solution. So thus complementary solution or transient response, transient response of the circuit RL is IT equals to C1 e to the power minus T R by L. This is the complementary solution. Particular integral. So particular integral is IT equals Vs sin omega t by R plus LD. One of the formula is, so say this is V function by d plus a, which can be rewritten as e to the power minus at e to the power at v by d. So this is the basic equation, this is the basic formula. Okay, we are gonna use this in this. Also we know that sine can be represented in terms of complex exponentials. So sine omega t is j omega t minus e to the power minus j omega t by 2j. We're gonna use this fact and the formula. So we also have another formula for exponential terms in when solving the particular integrals. E to the power ax by fd. Fd is the function for differential, the differential terms. So it can be written as e to the power ax by fa, given fa not equals to 0. So we are gonna use this 2 and the other formulas also. Now let us use the formulas. So v is by 2j e to the power j omega t by, so I have so d plus r by l, so like this, and e to the power minus j omega t by d plus l. So this is the situation here. So vs by 2 j l will and from the formula we get e to the power j omega t by j omega plus r by l minus e to the power minus j omega t by minus j omega plus r by l, which will give, say, v is by 2jl e to the power j omega t by r plus j omega l minus e to the power minus j omega t by r minus j omega l, and we have l. So if we take the common term from l from these two, it will give l. So should cut out this, and so let us define impedance z equals to r plus j omega l, and z prime equals r minus j omega l, which can also be written like this: j z in in complex or phasor form, which can also be written like this: phi, where phi is tan inverse omega l by r. This is z minus phi. Now let us use this, and the diagram is like this. So this is the real axis and this is j. This is the horizontal part is r and the vertical part is omega l, or j omega l, sorry, j omega l, and this is phi. So real. So we are gonna use these terms to solve our equation now. Now let us write it down. So v is by 2j e to the power j omega t by this is z, r plus j omega l can be written as e to the power z uh, phi minus e to the power minus j omega t by z minus phi, and if we take the common term out, which will give 2j z, the magnitude, and e to the power j omega t minus phi. So if you have studied phasors or polar forms, the polar forms can also be written in Euler terms. Okay, so z omega t sorry, z phi is the same as z e to the power j phi. Okay, so you can write it like this: minus e to the power minus j omega t minus phi. so which can be very easily written as z, and if we take the 2j term into the brackets, inside the brackets, so we will get e to the power j omega t minus phi minus e to the power minus j omega t minus phi by 2j. Now it has become obvious that this will give v is by z, and this is sine omega t minus phi, and this is the answer. So this is the particular integral for the RL circuit, for the RL response. Now let us find the complete solution for the RL circuit, series, for the series RL circuit. Okay, so complete solution or complete response, complete solution is IT equals, I say, the transient term plus the steady state term. The transient term is the complementary solution, the steady state term is the particular integral. So c1 e to the power minus r by lt plus vs by z sine omega t minus phi. This is the now we have to find the arbitrary constant. So we know at it equals 0 is the initial value, so it equals 0 is io plus c1 to the power 0 plus vs z sine minus phi. Thus we get c1 equals io, so sine minus phi is minus sin phi, so plus v is by z sine phi. So this is the particular, so this is the arbitrary value, this is the value of arbitrary constant. If we replace this, let me write here, so it equals io plus v is by z sine phi to the power minus r by lt plus the particular integral v is by z sine omega t minus phi. So what we are seeing is, for sinusoidal input the output is also a sinusoidal, because the transient response will die out, leaving only the particular integral or the steady state part. So the steady state part has the expression in sinusoidal form, but with a phase shift. Okay, so this is the answer in time domain analysis, the response of the circuit in time domain. So in frequency, so this is an LTI system. We can apply Laplace transform. So here R is frequency independent, so it will remain the same, but L is frequency dependent, so it will change into SL. And we have assumed initial current, so let us use the voltage analogy for the this transformation. So if we use the voltage analogy, this will give minus plus this is LIO. And for the sinusoidal input, the Laplace transform gives Vs sine omega t is omega by s square plus omega square. So you can see it in the list of Laplace transform, for list of formulas of Laplace transform. So this is the transformed circuit in frequency domain, where S is the complex frequency. Okay, so we are gonna use KVL likewise here. IS, so for IS, R plus SL IS equals Vs omega by s square plus omega square. Equation for voltage across the inductor, Vs is SLIS SLIS minus LIO, where IO is the initial current. So we're gonna use this. So we're gonna put this in the, so for initial current in the inductor, when the Laplace transform is done, the voltage across the inductor gives Vs is SLIS minus LIO. So in by KVL, the transformation will give the equation R plus SL IS minus LIO equals Vs omega by s square plus omega square. So R plus SL IS minus equals Vs omega by s square plus omega square plus LIO. Now IS is Vs. Let us for the moment uh, s- the s- let us keep the Vs and omega to the side, and let us put the Vs and omega to the side for the moment, and we are gonna use 1 by s square plus omega square R plus SL plus no plus L IO by R plus SL. Now for this part, what are we gonna do is we are gonna uh, break this apart in partial fractions. So let us break this term partial fractions. Say the term 1 by s square plus omega square r plus sl is of the form a by r plus sl plus bs plus c by s square plus omega square, which will so let us multiply the two this equation by s square plus omega square into r plus sl, which will give a 1 equals we're multiplying this, okay, this part by with this and the in the right. So 1 a s square plus omega square, or let us the have the denominator in the right side. So bs plus c r plus sl. Now if we see, say if we let use the value s equals to s equals to minus r by l, if we use this value, it will give us 1 equals a r square by l square plus omega square plus 0. No, a equals l square by r square plus omega square l square. Now let us equate the coefficients of s square and s. Okay, so for s square the coefficients will give a plus bl equals 0, which will give b equals l by r square plus omega square l square. Also minus, there will be also minus. And for c, so if we look closely for c, if we equate the coefficients of s only, we get b r plus c here. Sorry, we now if we equate the coefficient of s, we get b r plus cl equals 0, which will give equals r by r square plus omega square l square. Now we have got our value for a, b and c. A is l square by r square plus omega square l square. B equals minus l by r plus omega square l square, and c equals r by r square plus omega square L square. Now we are going to use this to find the value. So here Vs omega is A by R plus SL plus Bs plus C by S square plus omega square. And here LIO by L S plus R by L, which gives us Vs omega L square by L S plus R by L R square plus omega square L square plus minus L by R square plus omega square L square S plus R by R square plus omega square L square by S square plus omega square plus LIO by, sorry, so cut out, so IO by S plus R by L. Now here, so let us take the common out from the parts in the inside the bracket, third bracket. So here Vs omega R square plus omega square L square, which will give, so L, this L will cut out, so L by S plus R by L minus SL by S square plus omega square plus R by S square plus omega square plus IO by S plus R by L. Now here what are we gonna do is we're gonna use the earlier definitions. So Z is R plus J omega L, or this is Z e to the power J phi. Phi is tan inverse omega L by R, and so on. So and we're gonna do some modifications. So Vs by, so here Z equals root over R square plus omega square L square. So here it will be Z square, and if we take the omega inside the bracket, it will be omega L by S plus R by L minus omega L S by S square plus omega square by plus R omega by S square plus omega square IO S plus R by L. So now what are we gonna do is, so let us Define omega L. Omega L is Z sine phi and R is Z cos phi, because we know that, let me add this here. So if this is Z and this is the horizontal side part, or the horizontal component is R, and this is omega L, then obviously the equation these relations hold, and this is phi. Now what we are gonna do is put the values in this. So vs z square z sine phi by s plus r by l minus z sine phi is by s square plus omega square plus z cos phi omega by s square plus omega square plus io s plus r by l. Now if we common out the z term, it will give z square z. Now we are going to do two things. First, we have already commoned out the z, the magnitude part of the impedance, and now we're going to do inverse Laplace transform. So if you see that the formulas for inverse Laplace transform, the s plus r by l will give sine phi to the power minus r by l t minus sine phi. This is the cos omega t plus cos phi. This is sine omega t plus io e to the power minus r by l t. Now what we're gonna do is, for this part we are gonna use the trigonometric formulas to give a more standardized form for this equation. So here is from this we get vs by z. Okay, now it will give us e to the power minus r by lt sine phi, and if we common out the minus term, it will give sine omega t minus phi plus io e to the power minus r by l. Okay, here it will be plus. Okay, plus. Now we have got our, so this will be plus. Okay, so if you analyze this, it will be plus sine omega t minus phi. For if you apply the trigonometric formula for this, sine a plus b, or sine a minus b is sine a cos b minus cos a sine b. So If we rearrange this, it will give us io plus vs by z sine phi, obviously, e to the power minus r by l t plus vs by z sine omega t minus phi. So this is the answer, this is the response of the series RL circuit in frequency domain. Oh, we have done the inverse Laplace transform, so is will become turn, it will return into it in time domain. So this is the uh, response of the circuit, the result in time domain after analyzing the circuit in frequency domain, which is the same as the result we found in time domain analysis. Now if we summarize this, so in TDA and FDA, both in time domain and frequency domain analysis, the response of the circuit after analyzing it gave us the solution or the response of the circuit. The loop current equals IO, which is the initial current of the inductor, plus Vs by Z sine phi e to the power minus r by l t plus Vs by Z sine omega t minus phi, where this is, say if this is the horizontal axis is the real axis and the vertical is the imaginary axis, vertical j. So and if this the position vector, this is z, so the vertical part will be j omega l and the horizontal part will be r, and this is phi. So where z is r plus j omega l, phi is tan inverse omega l by r. So this is the final response for sinusoidal input. So that's it for today. In the next video I'm gonna discuss about the behavior of RC series, the behavior of series RC circuit when sinusoidal input is present. So thank you for watching the video this far. If you have liked it, please like the video, subscribe my channel, and if you have any questions you can ask in the comment section. You can reach me, and if you have any problems you can also tell me about it. I'm trying to solve all kinds of circuits and systems, and that's it. Thank you.